So I'm Sam Pitman, I'm a PhD student, as you all know, and I'm working on this project probe. You saw the Christie Proton Therapy Centre earlier in a ovarian talk. They're providing the cyclotron here for this Proton Therapy Centre, and this project is a boosting extension, an upgrade, if you will, to this facility to allow for proton imaging in the same facility. As you saw, the building's already being built, so it's not like they can just decide to whack a synchrotron in there. We're limited in space. We've only got 3 meters, so it needs to be a high gradient solution as well, so I'll talk about that. You got quite a good explanation of the Bragg peak earlier by Mark from Varian, but the main point is that protons deposit their energy differently via the Bragg peak, and so you get this precise dose, high dose of energy in one spot. This fact makes it even more vital to know exactly where you're depositing the energy in the patient. So at the minute, it's really limited by knowledge of the patient density, how much energy are the protons going to lose in the tissue before the tumour. So at the minute in treatment planning, they'll leave a little margin of error around the tumour to ensure that you're not getting a Bragg peak in any healthy tissue, and the aim really is to reduce that margin. So what you want to know is the proton stopping power between the surface of the patient and the tumour. There's a couple of different ways that you can see where the Bragg peak occurred in the patient. One is prompt gamma. That happens sort of naturally as a side effect of proton therapy. When there's an interaction inside the patient, within nanoseconds there'll be a prompt gamma emission, and you can detect this and know exactly where that happened, and you get a sort of real-time signal. So this would be interesting for image-guided therapy and things like that, but you can't really use it for treatment planning. The patient has to receive a dose in order to be imaged in that way. It would be nice to be able to create images without giving the patient a high dose before the treatment. At the minute, they use CT to plan the treatment, and they convert from Hounsfield units. Naturally, this produces error. They use sort of lookup tables to decide how much energy the protons are going to lose in the patient before the tumour. So the idea is that imaging with the same particle that you're going to treat with, you reduce this error. Proton CT has better accuracy than X-ray imaging, and you get a lower dose because you use a higher energy. So the Bragg peak doesn't happen in the patient; it travels through the patient and happens outside in a detector. So this is the sort of thing. This isn't my research. I took this image from Pravda, but it's just to let you know sort of how they do it. Protons are sent through entrance detectors that give you an idea of the angle that the protons enter the patient, and then you have exit detectors for the same thing, and then that's where you want the Bragg peak to happen, and you can recalculate how much what energy you need to get the Bragg peak in the tumour that you're aiming for. So you need 350 MeV protons to image through anybody. The literature sort of varies. Some people say 330 MeV, 350. It literally depends on the size of your patient and where the tumour is, I suppose. But yeah, the Bragg peak absolutely shouldn't occur in the patient for imaging. So in order to use this in a treatment facility, you need to produce 350 MeV protons. The Christie facility you saw before has a 250 MeV cyclotron, so it needs another 100 MeV. Synchrotrons can produce this, but you know they have a huge footprint. They're bigger, they're more complex. It definitely couldn't be used as an upgrade to a facility. Cyclotrons can produce higher than 250 MeV protons, but then they sort of lose the benefits that make them so attractive to medical facilities in the first place, like their compactness and the high dose rate that's possible, enough current to be able to degrade it at the end. There's another solution, NORMA, the normal conducting racetrack medical FFAG. This can produce 350 MeV protons and was obviously designed specifically for medical. It's got benefits such as rapid treatment, but again, it's got a larger footprint than can be used for our particular application in the Christie, and it's not yet been demonstrated. So there's our solution, probe, a pulse LINAC upgrade. There's the image you saw before at the front, and we've got this little 3-meter space here to put in a high gradient structure and hopefully allow for an imaging facility in this 4th gantry here. So the Terra Foundation at CERN did a design for a similar thing with PSI, the Impulse project. It's the cyclinac idea again with the 250 MeV cyclotron and then boosting the protons for the imaging section of the facility. But they used lower gradient structures. They had 7 meters of space, lucky, and they used lower power and 25 megawatt per meter average gradient. We need about 55, so wouldn't be suitable. Terra, again, with CERN, have been developing high-gradient LINACs for proton therapy, not imaging. And they've got this backwards traveling wave structure that they're going to test soon. That achieved 50 megawatts per meter in simulation. Like I said before, we need a slightly higher gradient than that, and our beam dynamics studies show that we need a bit more transmission than what they get through there as well. For those of you that don't know, the power flow model is something that CERN came up with. It's this local field quantity, SC, they took from experimental data. They did a load of experiments on high gradient structures, and they fit the data and came up with this SC quantity to limit the peak fields and thus RF breakdown. So that's typically what has been used in recent years to limit the peak fields in RF cavities and to inform breakdown rates. So we used that, of course, and we came up with we did some simulations. We ranged the frequency. We used different frequencies. We weren't sure which one would be best yet. And we also changed the septum thickness. The septum is the part of the cavity that's in between the two cavities as such, where the gap is. And the smaller that is, the higher shunt impedance you get, the higher gradient you get. So it's not really sure how that scales with frequency. Lower frequency cavities are bigger, so you'd have a longer septum. So is it going to be a bit wobbly if it's too thin, you know? So we did some simulations at different septum thicknesses. But the point is, the gradients that we were seeing were really, really high, limited by SC and by the shunt impedance as well. We chose 50 megawatt clystrons per 3 structures, so around 14 megawatts per structure. We used that to decide what gradient we'd get out of the cavities we were simulating. We got these really high gradients, which is great, but then we looked at the peak fields and they were super high, way more high than we were comfortable with. I mean, it's known that we can achieve higher limits than the Kilpatrick limit and have been able to for a long time, but these were still even higher than that. There were high gradient tests, and again by Terra, I keep name dropping them. We looked at the data that they produced, yeah, these electric fields were far too high. So we then had a look at setting our own sort of limit for peak fields based on the data that they had gathered. We scaled their data to our pulse length and came up with around 200 megavolts per meter, probably could go a bit higher than that, but wanted to be conservative. So this graph here shows the sort of gradients we were getting when we were limited by the modified Poynting vector, that SC quantity, and then we dropped the peak fields down to here and lowered the gradient. It's worth noting that the graphs that I've showed you already as well were at a 3.5 millimeter aperture. To begin with, we thought we'd get an advantage by having a really tiny aperture. That also increases the shunt impedance and thus the gradient. And then we did a beam dynamic study, and these were the sort of schemes. We thought we could have a really tiny aperture scheme and get this really high shunt impedance, or we could open the aperture and need less focusing magnets in between sections and fit a whole extra cavity in, so thus lowering the gradient requirement. And yeah, this is the scheme that we went with in the end. It's a lot simpler, and it turned out that we needed really strong magnets. It was completely impractical to do the small aperture scheme. So we widened then the aperture to 8 millimeters. And simulated different frequencies and different structures, and came up with this final structure here. We settled on S-band 3 gigahertz structure in the end. It's a side-coupled standing wave structure that operates in the pi/2 mode. Again, the septum, I mentioned it before, we did some studies and we found that the lowest that we would dare go to was 2 millimeters. We did some at 1 millimeter and got super high gradients, but then we decided when we're diffusion bonding and things, it's all going to morph out of position and it's not going to be practical. So we went to 2 millimeters because this has been built. It's been demonstrated before. I also looked at backward traveling wave structures, but I couldn't get enough group velocity through the structure, and this really limited my gradient, because you put coupling slots in the sides of the walls, and this degrades your shunt impedance. So it was limited by that. But this achieved a gradient of 54 megavolts per meter in simulation, 1 megavolt under what I wanted, but we'll see. I'm doing both the RF design and the mechanical engineering design of this cavity, and went on to do some thermal simulations. And again, back to the septum. Here's the septum, by the way. This little tiny thin bit here. It gives me a really high shunt impedance because it's thin, but it also means that the heat can't really travel from this hot bit here to the water cooling on the outside. So when you get a temperature gradient across the structure like this, you get operational detuning, which you don't want. So to limit this, we're going to limit the average power to 2 kilowatts. Which is fine. You get a lower transmission at the end of it, but we're talking to the Christie and experts in this, and they're happy with the current that we come out with in simulation. So I've produced mechanical drawings. I plan on manufacturing this structure in discs, chopping it up and diffusion bonding the discs together. Normally, or what has been done inside coupled structures before, they cut straight down the septum. And then, of course, I'm back to my 1 millimeter septum problem if I slice it down the middle. So a bit of an unusual slice to try and keep the septum intact here. But I had a meeting with a couple of CERN engineers yesterday, and they're unhappy about this little hole here. It's not really accessible with tools, and it's rounded, but I'll move on to that on the next slide. So there are some design features that I quite like. You may have seen there's a pipe, almost like a beam pipe running through the side coupled cells, which is unnecessary because there's no beam there, there's no field there either. But in order to tune the structure, I thought you might need to measure the field in these cells when you're tuning it. So that's what they're there for. But they also double up as a cute alignment feature for when it's being machined and stuff, a point of reference even. So that's a feature. You can see holes for tuning pins here to go on both the accelerating cell and the side coupled cell. There's a interlocking system here as well to help with alignment. Normally they'll produce, well at CERN anyway, they'll produce circular discs, and they use these V blocks to make sure you get alignment throughout the structure, but using a rectangular disc, you can't use that anymore. So we're playing with alignment features, and we're going to produce 3 prototype cells and bond them together to see what the alignment's like at the end, and also do a vacuum leak test on it. This is what I was talking about before with that coupling slot. The mechanical engineers were like, yeah, we can round it, but maybe it won't be as you expected. It won't be uniform, or it'll be really, really difficult. But it's quite a critical area. You get this magnetic peak field on the slot here, and it's a pulse structure. So if you pulse it, you're gonna end up wrecking the structure with magnetic heating there. So the idea is maybe to go to this sort of structure where you make the side coupled cell longer. It spans 2 cavities, and you in effect get rid of the coupling slot entirely. The top of one cell just runs into the next, and it's easier to manufacture, and also you keep that thin septum intact as well. I mean, side coupled structures have been made before, but not really at such high gradient. There was the Lebo structure, but that was much lower gradient, and that just had sharp coupling slots because they didn't have such high fields there. But yeah, so perhaps we'll go to this design. We plan on building a prototype cavity, an 11-cell prototype cavity as well. The final system would have 6 cavities with matching sections in between, but we plan on next year testing, doing a high gradient test and adding to those data points I was talking about earlier. There's a backwards travelling wave being tested as well. So it will be good to add to that field and better understand peak fields and high gradient breakdown. So yeah, thank you.
Okay, so any questions for Sam?
Everyone spoke to me at the poster.
Yeah, everyone's already spoken to her. Ah, yeah, someone from the medical community.
So I understood you're going to have 6 of these accelerating structures. And do you account for the protons getting faster as they travel through first?
Yeah, the beta will change. I mean, in the prototype cavity, I've only done 1 beta, but yeah, you'll account for that. You'll change the length of the cavities as you go on. Each cell will be individually designed for that.
And another question, you said you're going to deal with 2 picoamps of proton current?
Yeah.
Okay, that's another advantage for us to provide 2 picoamps of proton current.
Okay, thanks. Any other questions? No? Okay, well, thank you, Sam.
Thank you.